When we're trying to describe charge distributions, there's a couple of definitions that we need to understand. First of all, if charge is distributed all throughout the substance of an object, like this only works for insulators because for conductors it's all on the surface, but for insulators you can have charge all throughout this thing, on the inside, on the surfaces, everywhere. So for those kind of situations, we have to use what is called the volume charge density, rho. When it's distributed throughout a volume, we have to use volume charge density. Symbol rho is just Q over V. It's measured in coulombs per cubic meter, and there would be basically a density of charge in this whole thing. Now, especially with conductors, although we can do it with insulators as well, it's more common to have the charge distributed across a surface area A. For example, if I just rub this with my shirt right here, this becomes charged only on this surface, not on the back or the sides, just on a surface. So when we're talking about stuff like that, Q distributed over an area A, we use sigma. Sigma is the surface charge density. Q divided by A, that's a sigma right there, lowercase sigma. You can also have a situation where charge is distributed across a line, for example, a string, where the charge, there's so many coulombs per centimeter, so many coulombs per meter along a line of charge. So for that, we use the linear charge density, Q distributed over L. Linear charge density lambda is just Q over L. Now, it doesn't always have to be a constant like that. For uniformly charged, in other words, where the density is the same throughout, either the volume density is the same throughout, or the surface charge density, it's all evenly distributed along surface, or the linear charge density is a constant, where it's like every centimeter this has 1 microcoulomb. Those are all uniform densities. You can also have non-uniform densities. For example, if I charge this pith ball here, there might be more charge at this end, and the charge might get less and less and less as I go to this end. In that situation, I would have a variable charge density. Typically, we only deal with that with AP Physics C, but if you have a non-uniform charge density, rho, the volume charge density, sigma, the surface charge density, and lambda, the linear charge density, they do not have to be constants. They may be variables that depend on space. In other words, they may depend on X or R. So when we're doing that in AP Physics C, we have to do integrals. Notice that dq, the little infinitesimal charge, dq, if you're integrating over a volume, would be rho times the volume element dv. And our challenge becomes, how do we express dv, that small volume element? That depends on the shape. If you're talking about a surface, dq could also be expressed as sigma times dA, and that's so the area element dA. And the challenge is, how do you express dA? Or along a line, you would have dq as lambda times dx. So that's what we kind of need to describe charge distributions, and what we'll need. So that's all we actually have to deal with for AP Physics 1 or 2. But for AP Physics C, we have to now be able to do integrals to determine fields around some uniform and non-uniform charge densities. So that'll be in the next video.